Okay, good morning. So we finished this lesson today, and I will publish another quiz on weekend. Okay, so this would be the third one, and then probably we will continue with this matrix theory, but a new topic. Okay, so I don't know how much do you remember. We defined an operation last time, and that is the transpose, doing a transpose on a matrix. Yeah, so if you have a matrix A, for example, 1, 2, 3, 4, 5, 6. So do you remember? The transpose of this matrix is denoted by this symbol. It is the matrix whose rows and columns are interchanged, yes? So it means that this is the first row, so you write it as the first column. This is the second row, you write it as the second column. And this is the third row, so you write it as the third column, yes? And we learned some rules regarding this. For example, we learned that if I have a matrix, I transpose it once and transpose it again. It's not hard to see what will I get. I will get A itself. And then we also learned that if I have a number R is a number, I multiply it by a matrix, it becomes a new matrix. If I transpose this new matrix, it becomes equal to transposing the matrix first and then multiply it by R. So I told you that it is better to understand what is the meaning of the formulas that you write. So this tells you that if you multiply a matrix by a number first and then transpose, it becomes equal to if you first transpose and then multiply. Yes? And then we also had another important formula that if I have the sum of two matrices, of course these two matrices should be of the same order so that we can add them and then take the transpose. There is a simple relation, and this means that if you add first and then take transpose, it doesn't matter if it would be the same if you transpose first and then add the transposed matrices. And of course, this is the same for subtraction. And then, of course, we can combine these two formulas into one single formula and saying that if R and S are numbers, and I'll multiply a matrix A by R, another matrix B of the same order as A by another number S, and add them together, and then I want to transpose this combination, then it becomes the first one transpose plus the second one transpose, but the first one transpose uses this rule. So if you combine these two rules, it becomes RA transpose plus SB transpose. Yes? Okay. If I choose R equals to -1 in this case, what happens? I will have -1 times A, which means minus A, and then transpose, and then R is -1, so I get minus A transpose. So if you don't need a pair of brackets, they are the same. But what was the most important relation that we actually proved that in detail, if you remember, is that the product. Yes, what happens for the product? If I have A and B are multiplicable matrices, and then you want to multiply them first and then transpose. Do you remember what will happen? Yes?
Did it switch, please?
Yes. So it becomes transpose of each one of them individually, but in the reversed order. Yes? So this becomes B transpose A transpose. We actually proved this rigorously using the sigma symbol for the product. So that's a very important property. And then using mathematical induction, you can prove it for finitely many matrices, not just two matrices. For example, if you have A1 times A2 up to times AN, and then you want to transpose it, Of course, provided that this multiplication is defined, then you can transpose them, but you have to reverse the order. So you start from the very last one, transpose it, and then multiply it by the previous one transposed, and then you continue, then you reach to A2 transpose, and then finally A1 transpose. Yes? So all of them we discussed. And then one very important consequence of that is that what happens in this formula if all these matrices are equal? So all of them are equal, say all of them are equal to the same matrix A. So if you write this formula, what happens? Instead of A1, I put A. Instead of A2, I put A. And I continue, instead of AN, I put A, and then take the transpose. Okay, on the right-hand side, I will do the same thing. AN is A, transpose, and then A2 is A, transpose, A1 is A, so I have A transpose. But if I ask you what is a better name for this combination, because this is the same matrix multiplied by itself n number of times, this becomes A to the power of n, and then transpose. But if I ask you what is a good name for this, because you see that this is this matrix, which is multiplied by itself n times, so this becomes this matrix to power n. So that is a very simple but nice relation. So it means that you can interchange these two operations. It doesn't matter if you raise to power n first and then transpose, or you transpose first and then raise to power n. That's a very simple but very useful relation. And of course, if I ask you what is the transpose of the identity matrix, what is that? Yes? The identity matrix itself. But we can generalize it a little bit more. Any diagonal matrix, its transpose is equal to itself. So if D is diagonal, then D transpose is equal to D itself. Because you remember, hopefully, that if you have a square matrix, when you transpose it, the entries on the main diagonal remain the same. It will not be touched, yes? So this I have forgotten to put in the notes, I don't know. But any diagonal matrix, the transpose of any diagonal matrix is equal to itself. Okay. Now, there are two terminologies I want to introduce you here today. So, this definition, a square matrix A is said to be symmetric if its transpose is equal to itself. If this happens, that matrix is called symmetric matrix. And it is called skew-symmetric if the transpose of it is equal to negative of itself. Yes? So, for example, let me write this here on the board. Okay, so if you look at these two matrices, if I ask you to determine A transpose, you are supposed to interchange rows and columns, yes? Rows to columns and columns to rows. So this is the first row, I write it as first column. This is the second row, I write it as the second column. And this is the third row, I write it as the third column. But you see nothing has changed. Yes, this transpose is exactly equal to itself. So this matrix A is a symmetric matrix. Of course, symmetric with respect to the main diagonal. Yeah, so it means that if you don't consider the main diagonal, these are symmetric. Yes, so these two are the same. These two are the same. And these two are the same. Yes? And of course, it is clear that for transposing a matrix, I can have a rectangle matrix, but rectangle matrices cannot be symmetric, yes? And a skew-symmetric matrix, we do the same thing. I determine the transpose of this matrix. So I take this row and write it as the first column. This is the second row. I write it as the second column. And this is the third row. I write it as the third column. But you see, this is not exactly equal to matrix itself, but in this case, it is negative of the matrix. Because if I ask you to calculate negative of A, then this becomes 0, minus 2, 4, 2, 0, 5, minus 4, minus 5, and 0. And then you compare them, they are equal. So this means that this matrix A is a skew-symmetric. Now my question for you is that what can be said in general about the entries on the main diagonal of a skew matrix, a skew-symmetric matrix? Is there something that we can say in general for the entries on the main diagonal if you have a skew-symmetric matrix? Yes? All of them should be 0. Yes? Why is that? So you see that. So it means that if one of them is not 0, it cannot be skew-symmetric. But why it should be 0? Because, so you know that A transpose, if A is a skew-symmetric, it means A transpose is equal to minus itself. Okay, but now let us say I is an index between 1 and n be the order of the matrix. Okay, so A, now you know set theory, so let me just write I belongs to the set of 1, 2 of n. Yes? Okay, now if I ask you what is, so this means that if this one is equal to this one, the entry number II of this matrix should match with the entry II of this matrix. Yes? But how can I take this T? Do you remember? This is the meaning of transpose. You need to interchange the roles of the row and column indices. So I take this out, but I have to interchange these two indices. But both of them are the same, so if I interchange, nothing will happen. Yes? Yeah, in principle, I have used all the, let me just stick to my convention. I used these square brackets. And you already know that minus A entry, I can take this minus sign out. Then I move this to the other side. So this becomes 2AII is equal to 0. So this means that AII is 0. So for any I, AII is 0. So it means that if I have this assumption, I can prove that every element on the main diagonal is 0. Yes? So here I have put this as a remark here, it is good to know. So the entries on the main diagonal of a skew-symmetric matrix are all equal to 0. Okay, but now we need to solve some examples and then we are done actually for today's lesson. If we have extra time, we go back and solve some of the problems from the previous sections. Okay, so let us consider this example. Let A and B be square matrices of the same order. We don't know if they are symmetric or not, but we want to show that this combination and that combination, regardless of A and B being symmetric or not, it's always symmetric. Yes, so I have a matrix A, I have a matrix B, I don't know if they are symmetric or not, but I take this A and make this combination. I want to prove that this combination is always a symmetric matrix, regardless of if A it is or not. So let me solve this one, and then I will wait for you to solve that one. Okay, so we want to show that A plus A transpose plus A transpose is symmetric. So this is the question mark. So how can I show that this is symmetric? Because I don't have the elements. You see, if you have the elements, of course, you interchange the rows and columns and see if you generate the same matrix, yes? But if I want to show that this is symmetric, how should I do that? You need to refer to the meaning of what is the definition of a symmetric matrix. What was the definition? Itself. So this means that in order to show that this matrix is symmetric, I have to ask this question. Is it true that if I take this matrix and transpose it, it becomes equal to itself? If the answer is yes, then it means that this matrix is symmetric. Yes? But how should I prove this? So I start from the left-hand side. I have the sum of 3 matrices, and then I want to transpose the sum. I just reminded you today that you can separately transpose them. Yes? So you can transpose the first matrix plus you can transpose the second matrix. The second matrix is A transpose itself. I transpose it once more, and then I transpose the third matrix, which is A transpose. So first tell me, is that understandable? Yes? Okay. Now, for A transpose, I cannot do anything because I don't know A, so I have to keep it. But for this one, what can I write? A transpose, again transpose. It is just A. But for this one, we also learn the rule because that's the product. I want to transpose a product. Can I do that? Yes. I can do it individually, but I have to respect it to change the order. So I will start from the last one, which is A transpose, and transpose it, and then multiply it by the transpose of the first one. Yes? Okay, but these two, this is addition, so it is commutative, so I can write A plus A transpose. It doesn't matter order. But again, A transpose is what? Is A, and then I have A transpose left, and this is exactly, you see, I took the transpose of this one, and it becomes equal to the right-hand side. So I was able to prove that regardless of if A is symmetric or not, this combination that I construct from a given matrix is always symmetric. Yes? So I want you to do the same thing. So if I go back to notes, so do it for this one, and I want you to, yeah, you can solve that. I want to give you a little bit of time. The last one is a little bit hard. Okay, we can do it together, but I think you can start doing these exercises here. I want to give you time. Please try to write it down properly. Okay, could you solve the problems? Yes or no?
I didn't solve the last one.
The last one, you mean 147?
Yes, I solved the other one.
No, this is a little bit hard problem. But the other ones, I don't think they are hard. We're just using the properties of transposing matrices, yes? So let us actually start doing them. The second part of the example 144. So we have two matrices A and B, of course, of the same order. We want to show that this combination A, B transpose plus BA transpose. We want to show that this combination is always symmetric, regardless of if A and B are symmetric or not. So again, if I want to prove my claim, I need to take a transpose from this matrix and to prove that this becomes equal to the matrix itself. If I succeed to do that, it means that this matrix is actually symmetric. Yes? So what should I do? So I start from the left-hand side. So I have the sum of two matrices, then I want to transpose the sum. This tells me that this is possible to transpose the first one, transpose the second one, and then add the results. But this is a product, so if you want to transpose a product, you can transpose them individually, but what you need to be careful about is to reverse the order. So this becomes the second matrix transpose, and then A transpose, plus this the same. So this becomes A transpose, transpose, and then B transpose. But again, we know that B transpose transpose is B, and then multiplied by A transpose. And similarly, this becomes A, and this is B transpose. But this is commutative, so I can interchange these two. And this is equal to the right-hand side. Yes? So this is an exercise that you actually need to know about the rules. Yes? Okay, so for the other matrix, again, so the other example here, 145, A and B are symmetric matrices this time. Okay, so I start with symmetric matrices and I construct a new matrix in this form. We want to show that this matrix is again symmetric. Okay, so A and B are symmetric. What does it mean? It means that I already know that A transpose is A because it is given to me that A is symmetric. The same for B. B is symmetric, so I already know that B transpose is equal to B. And then I want to have this combination. B to the power of 4, A to the power of 3 plus, I think the other way around, yes, A to the power of 3, B to the power of 4. I want to show that this matrix is symmetric. So in order to show that the matrix is symmetric, I have to transpose it and convince myself that this is exactly equal to the matrix itself. Okay, so I have to use the rules. Yes? So what are they? I have the sum of two matrices transposed, so the left-hand side becomes equal to the transpose of the first one plus the transpose of the second one. Yes? But then I have the product of two matrices. I can take the transpose, but I have to reverse the order. So A to the power of 3 is the second one. I write it the first one and then transpose it. And then I have B to the 4, which is the first one. I write it as a second matrix and then transpose it. So the same is true here. So let me just write it quickly. But then, which rule do you think I will use now? So here I use the rule for addition, and then I use the rule for multiplication. And what I'm supposed to do you think? Yes?
Power group?
So it means that I interchange them, yes? So I was able to, I hope that you remember that I can interchange the power and transpose, so it becomes A transpose to the power of 3, B transpose to the power of 4, and then similarly here. Okay, but how can I continue? Because I started with symmetric matrices A and B, I know A transpose is A, I know B transpose is B, so wherever I see A transpose, I replace it with A, and wherever I see B transpose, I replace it with B. But you all know that you can interchange them because it is commutative. This, do I need? Yes, I need to change. So this becomes B to the power of 4, A to the power of 3, plus A to the third, B to the fourth, and that is equal to the right-hand side. Yes. So these kinds of exercises is actually a good exercise to work with theorems to be able to remember them. Okay, now let us go to this problem. Let A and B be commuting skew-symmetric matrices of the same order. We want to show that AB is symmetric. Okay, so we start with A and B, they are skew-symmetric, and we know that they are commuting. We want to show that AB is symmetric. Okay, so we know that A is skew-symmetric, so this means that A transpose is minus A, B transpose is minus B. Yes? Okay, my goal is to show that AB is symmetric. So what should I show? I should show that its transpose is equal to itself. This is the question mark. But of course, I know something more. I know that A and B are commuting, so there is no difference between AB and BA. So these are my conditions. Okay, so I start from the left-hand side of that expression. So this becomes AB transpose. I can write it as B transpose A transpose, but instead of B transpose, I put minus B. Instead of A transpose, I put minus A. But when I multiply them, it becomes BA. But because of this assumption, I can also write it as AB. And then it becomes equal to the right-hand side. Yes? Okay. Now, let us go to this problem. Let A be a square matrix. Show that the trace of this combination is always non-negative. So even if you have a matrix A, which includes a lot of negative entries, but still, if you calculate the trace of this combination, it's definitely non-negative. And importantly, we want to understand when it becomes zero. There is only one case that this combination, this trace of this combination can be zero, and that is if you start with the zero matrix. So we want to prove that. By the way, it's not a hard problem. For example, whenever you face a hard problem, you need to break the problem. So for example, the first thing might be I do if I don't know how to solve it, I start with a special case to see how it goes. And the simplest case is that I take a square matrix of order 2 to see how it works. I want to give you some idea here, but I want to wait for you to see how you solve the problem yourself, okay? So let us, for example, investigate something on the board. So A is supposed to be any square matrix. I want to show that the trace of AA transpose is always non-negative. Okay, let us, for example, to understand the problem, let us start with the simplest possible case, an arbitrary 2 by 2 matrix. Yes?
Or you can continue.
Yeah. And then let me calculate A transpose. A transpose means that replace this as the first column and just put this as the second column. And then, of course, I want to multiply them, AA transpose. So I take this row, these rows, and then these columns. I multiply this row by that column. So what will happen? This A will multiply by that A, this B will be multiplied by this B, and then I have to add them. So what happens? It becomes A squared plus B squared. Okay, and then I will take this one multiplied here, so this becomes AC plus BD, and then I will take this one multiplied here, so it becomes AC plus BD. Yes. And then I multiply this by that, it becomes C squared plus D squared. And now if I ask you what the trace is, what is the trace? The trace is the sum of the entries on the main diagonal. So this becomes A squared plus B squared plus C squared plus D squared. And then the problem is finished, yes? Because we want to show that this number is non-negative. So A, B, C, and D, of course, can be negative, but A squared, B squared, C squared, and D squared are all non-negative numbers. And when I add them up, definitely it is non-negative. Yes, is that clear? By the way, it's a very nice relation. So if you start with A and calculate the trace of this combination, you are adding all the sum of the square entries, yes? So A squared, B squared, C squared, D squared as a sum. So this combination is a very, so might be you were not able to guess if you want to do something with matrices to generate the sum of the squares of all entries, this is the operation that you need to do, okay? And of course, the second part is also clear. We want to show that the trace A of A transpose sometimes becomes zero, but when it becomes zero, this becomes zero if this combination is zero. But this combination is zero under one circumstance, and that is all of them are zero. Yes, because if one of them is not zero, then that one is positive, and when you add it with non-negative numbers, it becomes definitely greater than zero. So this is clear that trace of this is zero if and only if A squared plus B squared plus C squared plus D squared is zero, if and only if A is equal to B is equal to C is equal to D is equal to zero, and this means if and only if the matrix is actually the zero matrix. So by the way, this is not a hard problem. This is exactly the problem for the case of 2 by 2 matrices. But I want you to go back and forth to refresh your memory to be able to prove this for a generic n by n matrix. If you want to do the same thing for an n by n matrix, because it is not mentioned what is the order of the matrix, this is essentially the same thing, but you have to deal with sigmas a little bit and things like that. So I want you to try to refresh your memory and be able to solve that problem, okay? I will wait for you a little bit more, and then we can continue together. So what I want you is to write, consider that A is n by n, and write a formula for this. Okay. Could you write it down? Yes. So if you want to write it down, let us take A to be n by n, yes? So if I want to calculate the trace of A transpose, so what should I do? The trace of any matrix, so is the sum of the main diagonals, yes? Entries on the main diagonal. What is the meaning of the main diagonal? It means that I take my matrix, whatever it is, but I am interested in the entries of the main diagonal, meaning that the row and the column indices are the same. And I goes from 1 to the order of the matrix. Yes? This is the meaning of the trace. So, but then I have a sigma, I goes from 1 to n, but this is the product of two matrices, and I am interested in some entry of that, a particular entry of that matrix. So if you remember, that is another sum. But how should I fill up the sum? I need an index for the counter of the sigma, so let me take it k as usual. It goes from 1 to n, because this is a square matrix, all of them are n. And then what happens? I take this matrix A, I take this second matrix, but then I need to fill up these indices. So what are the indices for the first one?
Was it IK?
Ik. What is for the second one?
KI?
K, which again I, yes, exactly. Let me continue. So I goes from 1 to n, and then I don't need a pair of brackets. So then I have k goes from 1 to n. For the first one, I just write a ik, but what can I write for the second one? I have a transpose here. I can eliminate the transpose, but the price that I pay is that to do what?
Switch IK.
Yes. This becomes a, but then if I switch I and k, it becomes ik again. Yes? But this is a number that is exactly the same number. So these two numbers are multiplied. So if I multiply them, it becomes sigma I goes from 1 to n, sigma k goes from 1 to n, and then it becomes a I k to the power of 2. So that's this. That is actually done, yes? Because what is the meaning of two sigmas, you know? One index is the row index, one index is the column index, and I am running both these indices from number 1 to the last one, number n. So this means that I am adding all these entries. If I ask you what is this entry, you would tell me that this is the entry on the ith row and kth column, which is squared now. But then you are running I from 1 to n and k from 1 to n. So it means that you really add all the squares of the entries of all the matrix. Yes? That's it. So that is actually, in the previous case, it was easier to see it in this form, but I hope that you understand these double sum that you get here is exactly what you see here for this 2 by 2 case. Okay, then it means that it is first of all clear that I am adding up a bunch of numbers, all of them are non-negative, so definitely this is non-negative. And if I ask you what happens, this is 0 if and only if that sum is 0. But this sum is 0 if and only if all the individual entries are 0, because the sum of non-negative zeros, the sum of non-negative numbers can be 0 only under one condition, and that is all of them are 0. So if I want to write it, I would say that for all I and k in the set 1 to up to n, a I k squared is 0. But this means for all I and k in the set 1 to up to n, a I k is 0. So it means that the matrix is 0, if and only if the matrix is 0. So this is the rigorous way of writing this in general. Okay. This is also good to know. Let's just see what does it mean. If I have two column matrices A and B, then it is very interesting. There is no difference between A transpose B and B transpose A. This is a very particular case. This formula is not in general true. Yes? If I have two column matrices, it doesn't matter if I calculate A transpose B or B transpose A. This is only for this particular case. That is not a generic rule. Okay, and I hope that this is understandable. Yes. So, for example, so if A is this matrix A1, A2 up to AN, and B is B1, B2 up to Bn. First of all, do you see that A times B is not defined at all? Yes? A cannot be multiplied by it because this is n by 1. This is also n by 1. I cannot multiply them because these numbers in the middle are not the same. But A transpose B is defined. And the answer is just one number. Yes? If I calculate A transpose B, A transpose is A1, A2 up to AN. And when I multiply it by B1, B2 up to Bn, then it becomes one single number. So I have to take this row and multiply it by that column. Then the A1 will be multiplied by B1 plus A2 will be multiplied by B2, and then it will continue until I have AN, BN. Of course, I have written this as a sigma. So this becomes the sigma A I B I goes from 1 to n. So if you calculate this combination, you get a number. And then you can easily convince yourself that if I calculate this combination, I will get the same number. But this is, I told you, this is exceptional. Don't take this for granted. This is nonsense usually if you write this in general. Okay, but in this particular case that the most matrices are actually column matrices, then this becomes B1 up to Bn, and then it becomes A1 up to An, and then you can continue and then you get the same number. Because this one, B1 A1 plus B2 A2, and then continue Ban. That's the same matrix. But what about these two? AB transpose. Is it doable to do this? AB transpose. B transpose is a row matrix. So what type of matrix is this matrix now? A is this, B is this, and then I want to consider this AB transpose. So what type of matrix is this? Is this a matrix or not? Yes?
Square matrix.
N by N square matrix, yes? So, and then the same thing, if I have the other one is a BA transpose, that is also an N by N matrix again. But then there is no guarantee that these two matrices are the same. But it is guaranteed that the trace of this is equal to the trace of that. So this means that we want to show that the trace of AB transpose is equal to the trace of BA transpose. Even though in general the matrices are not the same. So how can we convince ourselves? And that is a very interesting thing. It means that the trace, it is very unusual formula. So this means that the trace of AB transpose is B transpose A. If they are column matrices, that's a very nice relation actually. So if you want to take the trace of AB transpose, you can write B transpose first and A coming after that, if they are column matrices. Okay, so how can we prove this? That's also a good idea if you want to think about it yourself. So try to convince yourself about, so this one I confirmed, this one is, so this one is equal to this one I confirmed. Yes? But still, we don't know why these are also equal to these numbers. That is a good exercise if you can try to prove that, for example, this one is equal to this one or that one, it doesn't matter. And then if you can do that, similarly, this is also equal to this one, then it means that all of them are equal. So that's a very nice relation if we have two column matrices. This is only working if we have column matrices. Okay, any questions? Yes?
Would it work for row matrices as well?
For row matrices, I think it should work. But then, of course, we have to interchange them. Yeah, because if I have a row matrix, so for simplicity of writing, let me just take them 1 by 2. Okay, so for example, assume that matrix A is AB and matrix B is CD. Okay, so in that case, A transpose B is actually a matrix this time. In that case, A transpose B was a number, the other one was a matrix. But in this case, A transpose B is a matrix, yes? So this is AB multiplied by CD, then it becomes AC, AD, BC, BD. And then the other way around, BA transpose is actually CD and AB. And when I multiply that, it becomes AC, oh sorry, this becomes AC plus BD. Okay? Now if I ask you to take the trace of this one, you get AC plus BD, so it seems to be right. Yes. But of course, you need to understand that you need to write the other way around, yes? In that case, A transpose B is a number. In our case, BA transpose is a number. But if you respect that, yes, that is also correct if you have two row matrices. Any other questions? Okay, thank you.